Good morning students. Today class we are going to discussing about the second part in a fifth unit. The second part in a fifth unit is linear systems with random process. In this part we are able to discussing the what is a linear system and what are the properties of linear system is having and how to respond on linear systems when applying the random process concept. In this random process concept, we are able to apply the input is the main value, what is the response of a system, and the input value is a correlation function, what is the output response. In correlation, we are having the two types, one is a cross correlation and second one is autocorrelation. When applying the autocorrelation function, what is the system response? Suppose we have to applying the cross correlation to the input of a linear system, what is the response? I have to discussing in this unit. First of all, we are going to discuss about linear systems. First, what is a system? System. Here we can consider the block diagram for that. Have to applying the input, otherwise the input is process, it will deliver the output. The input is process, it will deliver the output, is called system. Here I have to consider the input is x of t and output is y of t, and the system function I am consider h of t. What the system can do that, the system can take the input is raw material. Input is raw material. The raw material, it can be processing and it will be deliver the product. Suppose you can see how to make a cake. While making a cake, we have to choose the one machine. In that machine, we are injecting what are the materials is required for manufacturing the cake. In that, we have to injecting the materials like sugar and raw materials, what are the raw materials is required for making the cake, and we have to adding some sweetness and flavors. What are the flavors we are required, that those all are we are injecting to machine. The machine can do that, what is the layers it can be forming and how to do that, its shape. The complete output is the one cake. But the input is raw material like sugar and what are the material you have to giving to your machine. The machine, what it can do that, it can do some process. The process can making the products. The product will be output. See one more example. We are giving the input of a system is, we have to assigning one material. The material is, we have to see another example to a system. We are washing a cloth. The cloth is what are the dirty cloths is there. Those are the raw material. We have to injecting or we have to insert the machine. Before inserting that, we have to fill with water and we are adding with detergent. Then we have to put your what are the cloths is there, we have to keep in the machine. What the machine can do that, it can do some process. After processing, it will use the clean cloths. Here what are the processing on a raw material? Here the system can do the process. How it can be forming the raw material to our required material, that can be forming by the system. You can simply say that the system is a function that can make the output by using the input. The system function we are always representing with impulse function. Here coming to the linear system. What is a linear system? Which system can satisfy the superposition principle Which system can satisfy the superposition principle? We are said to be the linear system. What is the superposition principle conditions? One is a homogeneous and second one is a additive properties. Which system can satisfy these two conditions? We are said to be a linear system. Suppose here consider the system is, this is a system. For the system I have to assigning one input. The input is x1 of t, x1 of t. The system function is h of t, and when I have to apply the x1 of t, it will deliver the output is y1 of t. Output is y1 of t, the first case. And the second case, I have to take the same system, but in this case I am applying the input is x2 of t, input is x2 of t, output is or its response is y2 of t, y2 of t. Here in these two cases we are having the different inputs but the system is same. Suppose I had to give the raw material to a system is half kg. The product will be is only 400 grams. Suppose I have to give the 1 kg. What is the product will be there at the output side? Suppose the system is a linear. For half kg it is given the 400 grams. But after taking the 1 kg, it will be give 800 grams. There is a linear system property. The linear system, what the input had to change, the change will be there at output. At increasing that quantity, the output quantity is also be increasing. If the quantity is decreasing, the output quantity is also be decreasing. Here can saying in a mathematical orientation, we have to consider two functions. One function is the input and its response is y1 of t. In second case, applying the second input is x2 of t. In this case, the response is y2 of t. y2 of t. Now we can check the linearity of a system is, one have to consider x1 of t and x2 of t. We are adding these two inputs, we have to treat as a third input. Can adding the two inputs, we can treating as a third input. Now you can apply this third input as an input to your system. Input to your system. Its response is y3 of t. You can consider its response is y3 of t. The y3 of t is equal to, the response will be the function of input. The function of input. This is a function of input, I had to treating that. What is x3 of t? It's a summation of x1 of t plus x2 of t. x2 of t. Here, this is the third step. In fourth step, and treating as a is a y3 dash of t is equal to, what are the individual responses of each and every system on applying the individual inputs like x1 of t and x2 of t. Here the responses are is a y1 of t and y2 of t. Those responses we are adding is y1 of t plus y2 of t. y2 of t. Already here getting that, so y1 of t is equal to x1 of t and y2 of t is equal to x2 of t. x2 of t. Here you can replace in their corresponding quantities. Here y1 of t is x1 of t and y2 of t is equal to x2 of t. We can compare the y3 of t and y3 dash of t. Both quantities are equal. Both quantities are equal. Then you can set to be the given system is linear system. The given system is linear system. Otherwise, it is a non-linear system. This is the homogeneous property. You can take the additive property. Additive property means we have to multiply the quantity of input with some number. The same number is multiplying with its output also. Suppose here I am treating x1 of t is multiplying with a and x2 of t is multiplying with b, and its response is also b multiplying with a, and here also be b. You can adding here the a into x of t1, here b into x2 of t, and similarly you can writing here also a and b. Just we have to multiplying some quantity at input side. The same factor is multiplying its output also. Here also you can choose the multiply factors, so product factors. We can writing like this function. It is having the multiplying factor and homogeneous. Multiplying factor and homogeneous. The multiplying factor gives the additive property. Additive property. The additive property means we have to choose one factor. We can multiply the input. The same factor is multiplying its output. Based on that condition only, we have to set that the given system is a linear system. The non-linear systems, we are defining that which system is not satisfying. Which system is not satisfying the superposition principle we are said to be, it is a non-linear system. Otherwise, we have to simply say that the linear system or any system, it is a summation of weighted signals, summation of weighted input signals. Suppose here I am consider y of t is a output signal. It is weighted sum of input signals. Here I am taking the weighted sum of input signal is a1 x1 of t plus a2 x2 of t plus a3 x3 of t plus and so on plus an x suffix n of t. This entire sequence I have to represent summation of. Here I am treating n is equal to 1 to n is equal to 1 to n an xn of t. Always the output response we represent with is a transform of x of t. Here also you can add in this transformation. The transformation, here you can apply the transformation on this input function. We are applying the output. This is another definition for linear system, otherwise the system function. Linear system means which system is satisfying the superposition principle we can set to be is a linear system. The system response is defined is a weighted sum of their input signals. The system response always we are writing is a transformation of input. The response is y of t is equal to transformation of its weighted input signals. The weighted input signals we are writing like this, and then the transformation of is n is equal to 1 to n and its weighted sum of its input signals. And how to finding in general the response of a system? By using the impulse response. By using the impulse response, you can able to find in any system response. The impulse response we are denoting with del symbol. We have to take the system function is h of t is equal to the transformation of impulse function. It's a basic relation. We can able to find any system response by using the impulse response. The impulse response, it is a ratio. It is a ratio of output by input. output by input. Otherwise we have to able to define the transfer function. The transfer function also we are defining that it is a ratio of its frequency representation of output divided by its frequency representation of input. That one is a transfer function. Now we are seeing that concept. Coming to the next topic is a response of a linear system. Response of linear system. In the response of a linear system, we are mainly having the two types. One is the impulse response and second one is output response. We can obtain the linear system response in two ways. One is from impulse response and second one is from output response. Here the impulse response, we can able to find the convolution. The convolution is the basic property. By using the convolution property, we can able to find in the output response. Here you can find the response of a linear system. In that one method is impulse response. Impulse response. In general, in LTI systems, the convolution property is the basic property. You can obtain the output response by using the convolution. The convolution means we have to take the signals as the input signal and system function. Suppose here you can consider xt of t is input signal and h of t is a system function and y of t is output signal. The output response is always the convolution of input and system function. Input and system function. This is the formula for you can obtain the response of a system. Here, if del of t is a impulse function at the input, then the impulse response is h of t comma tau is equal to the transformation of impulse function. Otherwise, we can obtain this function. We can use in the convolution property. The convolution property is a basic property you can obtain in any system response and time domain. In time domain, the second method is output response. For output response of a system, we are obtaining by using the convolution property between input signal and system function. Here, the system function, I am treating the impulse. And how to writing this convolution property between this input and system function is I am deriving here. That is x of t is equal to x of tau is a del of t minus tau. Del of t minus tau into d tau is a convolution property. In that convolution property, it is an impulse function. It's a completely impulse function. By taking the transformation on this impulse or on this signal, have to writing the transformation is here we have to take the y of t. Y of t is equal to the convolution between x of t and del of t. By taking the transformation, the y of t is equal to the transformation of x of t. The x of t already we are writing is the integral minus infinite to plus infinite x of tau into del of t minus tau into d tau. Now I am applying the transformation on this function. Here I am considering the x function. The x function I am substituting as it is. I have to move this transformation. X of tau is not having the t, the small t time parameter. That's why I have to apply the transformation on only the time parameter. When I have taken the transformation on impulse function. It is gives the system response. The system response is h of t comma tau. Already we are seeing here. This one is a system response. This one is impulse function. The impulse function transformation is the system function. Now we can writing the system response in terms of their system function. This entire function we can writing in a shortest notation the convolution between x of t and h of t. We can obtain this relation. We have to consider the input signal is having the multiplying with impulse function. That's why I'm consider integral minus infinite plus infinite x of tau into del of t minus tau into d tau. In that function, I have to applying the transformation technique based on the system function. The system response is always the transformation of input. Based on that, I have taken the transformation. The transformation is only applying on time parameter, but not the tau. Tau is a time difference. Tau is a time difference. Now I have to applying this transformation on impulse function, and I have to take in the transformation on impulse function. It is representing the system function. Now I am replacing the system function in that equation. That equation have to set that it is a convolution between x of t and h of t and continuous time signal. Now we can go for another topic. That one is linear time invariant system. Linear time invariant system. The linear time invariant system, we are defining that which system input and output is not changed with respect to time. Suppose the time is changed, but the input signal and output signal is not changed. Can simply say that in LTI system, in LT, that's a linear time system. Linear time system is not, otherwise the linear system input and output is not depending on time parameter. Is not depending on time parameter. Is said to be linear time invariant system. Otherwise, you have to shifting the input signal time with the tau. The same shift can be done at output. Here you can see here the system function. Generally, we are writing y of t is equal to transformation of x of t. Transformation of x of t. The general system function we are writing like this. The output is the transformation of input. Suppose we can make some shift in a time parameter at input. At input I have to do some shift. The shift is tau. Shift is tau. The same shift is done at output. That is the y of t minus tau. Y of t minus tau. Then the system is said to be the linear time invariant system. The total function we can writing like the y of t comma tau is equal to y of t minus tau. Suppose he is given one system. The system is y of t is equal to t x of t. T x of t. Otherwise, we can take y of t is equal to x square of t. X square of t. Here, the system is a squaring function. The system is a squaring function. You have to take the system. Input is x of t. Is a squaring system. Squaring system y of t. The squaring system response is x square of t. X square of t. How to check the system is a linear time invariant or not? The system is a linear system and it is also a time invariant system. It can be said that we can take the y of t comma tau. T comma tau is equal to, what is the function we are having is x square of t. X square of t. Where x square of t is there, have to replacing x square of t. X square of t. The t is replacing with which function you can consider. Here t is a normal time, tau is a time difference. Tau is a time difference. You have to do that some change in a time parameter. Some change in time parameter. The same change will be appear. The same change will be appear on the system. On the system, we can set that it is a both are equal. It is time variant. Suppose those two are not equal. Here you can see the system function is this one. We can check it is a time variant or invariant. We are adding the delay before processing and after processing. Here I am consider the delay is tau. Delay is tau before the system. The squaring system is the output. This one is x of t. X of t. Have to add in the delay, have to writing x of t minus tau, x of t minus tau, and we have to give the squaring to this one. You have to writing is the y of t, y of t. The y of t, that means a response y of t. Otherwise, you can write the y of t minus tau or t comma tau. T comma tau is equal to the function is x square of t minus tau, x square of t minus tau. And second case is you have to add in this delay after processing. First you can take in the squaring function, then we have to assign the delay. So tau, delay is tau, the input is x of t and output is y of t minus tau. You can take in that. Here we are having the two statements, one is this and second one is this. Now we can assigning the squaring function at this point. At this point we are getting the x square of t. Then we have to give the delay. The delay is a tau. We can assign the tau x square of t minus tau. After processing, we can assign in the delay. Now this function is equal to the y of t minus tau is equal to x square of t minus tau. You can see here the y of t comma tau is x square of t minus tau, and y of t minus tau is also be x square of t minus tau. Both functions are equal. Both functions are equal. You can set that the system is a time invariant system. If it is equal, it is a time invariant. It is not equal, it is a time variant system. This is a condition how you can check the given system is a time variant or invariant. Invariant, the both quantities are equal. That is the thing we have to do here. We can check this condition, how to find this is y of t comma tau as well as y of t minus tau. We can find the y of t comma tau. We are given the delay before processing. Before processing, I have to give the delay to the input. For this system input is x of t, I have to assign the delay is tau parameter. That parameter I have to write is x of t minus tau. This delay input I am assigning to the system. The system is a squaring function. I have to squaring here. The function I am writing the y of t comma tau is equal to x square of t minus tau. Then second step is we can assign the delay function after the system function. That's why I have to give the x of t. X of t is assigning to the input of system. The system is squaring that, and the squaring function is x square of t. Once you can obtain the processing, we can give the delay. You can assign the delay only in function. Only in function. Before the terms is there, you are not assigning any delay. That's why where t is there, just you can blindly keep the t minus tau in that second step. So y of t minus tau is equal to x square of t minus tau. Then you can check it. So y of t comma tau and y of t minus tau both are same or not. Both are same. The system is a linear time invariant system. Both are not same. Both are not same. You can say that the system is a linear time variant system. Is a difference. You can identify the given system is time variant or invariant. Coming to the next topic. The next topic is a transfer function of a LTI system. Transfer function of a LTI system. The transfer function of a LTI system, we are finding that it is a Fourier transform. It is a Fourier transform of LTI systems impulse response. What is answer that? The transfer function of a LTI systems is defined as the Fourier transform of LTI systems impulse response. Here I am taking the impulse response is h of t. I am applying the Fourier transform to this. This one is called the transfer function. We can represent in mathematical orientation is a minus infinite to plus infinite. It's a h of t into e power minus j omega t into dt. Minus j omega t into dt is a function we have to writing like this. Then how to represent it in general? Suppose we can consider the convolution between input signal and output signal like this. So y of t is equal to the convolution of x of t and h of t. X of t is the input and h of t is a system function. System function. We can take in the convolution between these two signals. We can obtain the system response. But you can able to find the transfer function. You can apply the Fourier transform. You can apply the Fourier transform. According to the Fourier transform properties, the convolution between any two signals or more than two signals is equal to the product of their Fourier transforms. The convolution and continuous time domain signal, we can apply the Fourier transform on that. It is the product of their Fourier transform values. Here you can see the convolution of h of t and x of t. You can writing according to the properties of Fourier transform is y of omega is a frequency domain or Fourier transform of y of t, and x of omega, it is representing the Fourier transform of x of t. According to the property, these two are the products, the h of omega. From this relation, we can writing h of omega. H of omega is equal to y of omega divided by x of omega. From this relation, we can set that the transfer function is defined as the Fourier transform of output signal divided by the Fourier transform of input signal. This is the definition for the transfer function of LTI systems. We can treating as a LTI systems, we can adding the LTI. In LTI systems, the transfer function is defined as the Fourier transform of output divided by the Fourier transform of input. Now coming to the next topic is the stable systems. Any system response we can able to find by using the convolution, that is the y of t is equal to x of t, the convolution of h of t. By using this property, we can set that the system is stable or unstable. You can simply remember the stable system we are defining with, it is having the bounded input, the response is also be bounded. Bounded means is a finite. How to assign the finite input, the response is also be finite. The system is said to be stable system. Suppose we can say in terms of equations, we can write in the convolution. The convolution between these two is minus infinite to plus infinite is x of tau into h of t minus tau into d tau. In this function, what are the impulse function is there? We can treating as a minus infinite to plus infinite is a h of t or t minus tau. The value must be less than to infinite. We can set that the given system is a stable system. If it is not satisfying this condition, you can simply set the given system is a unstable system. This is the definition for stable and unstable system in our linear systems. Coming to the next topic is the causal systems. We are defining the causal systems on a continuous time signals. Suppose you can consider the continuous time signal is x of t. The x of t is said to be a continuous time signal and its system response is y of t. Here we are able to discussing about the LTI systems, the linear time invariant systems. The LTI system is said to be causal. When said to be causal, the output response is depend on present and past time input signals. Here the causal system of LTI, we are defining that which system output response is depending on the present and past time input values or input signals. We can set that it is a causal system. The causal system is a reliable systems. Reliable systems is always physically implemented. Coming to the another case. The another case is non-causal systems. The non-causal of a LTI systems, we are able to define in that The output response is depending on present, past and future time input signals. Which system output response is depending on present, past and future time input signals is said to be a non-causal system. The non-causal system is not reliable. That's why we are not physically implemented those type of systems. But we have to use this concept in memory devices. This is the how to define the causal system and what are the reliable and what are the non-reliable situations in causal systems. Coming to the ideal systems. Here the ideal systems we are defining that its frequency parameters. We can give the system function is h of omega. The h of omega we are representing with its magnitude. The h of omega modulus is representing its magnitude and its phase is represented with theta. Here the magnitude is increasing or decreasing with respect to their input. Suppose the input of a system is increasing, the magnitude is also be increasing. If the system input is decreasing, output is also be decreasing. Otherwise, the system magnitude is a constant. The system magnitude is constant. Here you can consider the system magnitude is a constant and phase. Here angle we are calling a phase. The phase is linear. With respect to its frequency. We can say that the system is ideal system. When I have to define the ideal system, its magnitude is a constant and phase is linear to vary with respect to frequency. We can say that it is ideal system. We can define this h of omega is equal to its magnitude is constant. Here represent the function like this. Coming to the next topic. The next topic is response of linear systems. To random signals. Here you can consider up to now we are discussing the linear time invariant systems, LTI systems. In that systems, how to find the system response and how to obtain the system response by using the impulse function, and how to finding the output response by using the convolution property. And you can see that some properties of systems like stable system, causal system, ideal system and time invariant system. These are the properties we are discussing. Now you can see when applying the random signals to LTI system, what is the response? The response we are obtaining here. Here the response of linear systems to random signal. Consider the LTI system is always stable and causal. Stable means it is having bounded input, bounded output. So finite input you can apply here, the finite response will be up here. That one is calling is a bounded system, otherwise you can call it a stable system. And the causal system. The causal system already we are discussing later. We are discussing in our previous session. What is a causal system? The causal system is the output response is depending on present and past input time signals or time input signals. You can say that is a causal systems. Now we can take this assumption we are having to defining the responses of your systems. Suppose you can take in that input is x of t, output is a y of t. Both are continuous. You can say that the system is continuous time signal or continuous time system. Suppose you can consider x of t and y of t. X of t is an input and y of t is an output. Both are discrete. In case of discrete, we are representing this in a small n's. x of n and y of n, y of n. The system we can call is a discrete time system, discrete time system. But here can define the nature. Suppose the random processes is x of t and y of t, both are continuous. The system you can set that it is a continuous time system. Continuous time system. Suppose the random processes is x of t and y of t, both are discrete. Both are discrete random processes or discrete nature. We can set that the given system is a discrete time system. Now coming to the system response. The system response, already we have said that the system response we can obtain by using the convolution. By using the convolution, the y of t is equal to the convolution of system function and input function. Function means here the signal. You can write in the convolution formula as a minus infinite to plus infinite, the h of t minus tau, h of t minus tau. Otherwise you can write in h of t into whatever the function you can consider the starting, you can write in as it is. The next function is x of t minus tau, x of t minus tau into data. This is a system response equation. You can find the system response, we can apply the convolution property on that input signal and system function. By using this, we can able to find the system response. Coming to the next topic is the mean value of output response. The mean value of output response. We have to take the mean value is an input. Mean value is a input. We can obtain the system response. For this, we can consider the output is y of t is equal to the convolution of input signal and impulse function. Otherwise, you can write in h of t is a convolution of x of t. You can write in any direction. Now we can write in the convolution formula integral minus infinite to plus infinite is h of t into x of t minus tau into d tau. Here you can apply the expectation on these functions, applying expectation or expected value on above function or above equation. Above equation, you can write in expectation of y of t is equal to expectation of the minus infinite to plus infinite h of t into x of t minus tau into d tau. This is a function we are having. You can move this expectation into inside the integration. How to write? It's not h of t, is h of tau. H of tau. Here you can apply the expectation where t is there. You have to apply the expectation, that is the integral minus infinite to plus infinite h of tau to expectation of x of t minus tau into d tau to d tau. Here you can writing the expectation of y of t, you can write in the y of t bar, y of t bar, and here the expectation of the x value is x of t minus tau bar is a constant. Why? Because it's a mean value. You can write in this will also be constant. That is y of t bar is equal to, I am writing the constant outside, so x of x bar, and just I have to give the notation of x bar. And here also can write in the y bar, but remaining term is minus infinite to plus infinite. Minus infinite to plus infinite h of tau into d tau to d tau. You have to take the Fourier transform on h of t. On h of t, you can writing the Fourier transform for h of t is integral minus infinite to plus infinite h of t into e power minus j omega t into dt. In this equation, I have to substitute the omega is equal to 0. Omega is equal to 0. Then I have to write h of 0 is equal to integral minus infinite to plus infinite h of t into e power 0 means 1 into dt. Here when I have taken the 0, that's the frequency value 0, its value is this one. Based on that, I have to replace the quantity in this equation. That is y bar is equal to x bar into h of 0. H of 0. From this we can say that the mean value of output response, is equal to the mean value of input is multiplying with its frequency response at frequency is 0. With its frequency or system function value at frequency is equal to 0. This is the response we are obtaining when I have to consider the mean value. We can obtain the mean value of output response. We can do this procedure.